Alrighty, there's Henry. People are going to start trickling in here soon, I'm sure. Very good. Sorry for the late link, guys. I'm a little bit behind myself this morning. All right, here we go. So folks are starting to trickle in. Welcome back to pre-calculus. Sorry for the somewhat late start, but today we are going to move forward talking about functions. At the end of the week, last week, we talked about how to get information from the graph of a function, specifically how to find things like domain range, intervals of increase and decrease, local maxima and local minima. Today, we are going to talk about something called an average rate of change, which is a really big deal. It's a big deal in this class because it's a useful concept for application problems and stuff like that. It's going to become an even bigger deal in Calc 1. This section 2.4 that we're talking about today, is going to be sort of the starting point for you to discover something called the derivative when you take Calc 1. In fact, you may remember last Friday, I mentioned that the reason we always use open intervals for the increasing and decreasing locations is because those intervals of increase and decrease are solutions to a certain inequality involving a certain special function, not the original function, but a related function. The way you begin to cook up that related function, which is called the derivative, is by writing down an expression for the average rate of change for the original function. And then you do some special calculus steps to that. So today I'm going to walk you through the first few steps that you will need in Calc 1 to go through that procedure. And we'll talk about the sort of natural algebra things. Let's see, I have a question here in chat. I'm not sure that I saw your message. I did manage to clear my whole inbox yesterday. So if it was in there yesterday, then I think I should have seen it. But if it came in, say, more recently than like 2 p.m. yesterday, then I might not have seen it. Is it something you want to talk about now?
This is partly a mistake on my part. I thought the homework was due today. So I was planning to do it yesterday and it turned out it was due Monday. I was just going to ask for an extension, that's why.
Yeah, no stress. So in general, when you need an extension, just hop over into WebAssign and within the assignment, let me see if I can see it in the student view. It may or may not show it to me. There's a little button there or a little link that says click here to request an extension. And if you ever need time on an assignment, regardless of the reason, just go ahead and click that link and put in there the date that you want it extended to. And I'll go in and grant these. About two times a day I run through and grant those. Let's see if I can show you where this is. Student view. All right, where is this? So maybe I want to come in here. All right, so somewhere on here, whoop, my mouse. You should have an option for request an extension. Yeah, down here. So if you ever need more time on an assignment, just come down to the very bottom here and click this link that says request extension. It's very, very rare that I deny an extension request. If you put a date in there that's like a month away, I might change the date to something a little more reasonable because usually I want you to get these things done within a day or two of the original close date or within a day or two of the extension request. But yeah, I'd be happy to do that. Just request an extension. I'll come through and clear those out a little later today and you get it. Okay. QQ. Oh, we already got QQ. Okay. So what are we saying? Average rates of change, right? I think there is one instance of a rate of change that everybody is familiar with, especially here in America where everybody drives so much, and that's speed. So that's the way I'm going to introduce this to you is by thinking about speeds. But before we get there, let me go through a few little announcement-y things. So of course, this is MAC 1140 section OR1, which is a pre-calc class. And today is the 8th of September, 2021. Today, as I said, we're going to talk about average rates of change. And because that string of words is going to show up a million times in today's lecture, and I don't want to write it out every time, I'm going to abbreviate it AROC, average rate of change. And this is section 2.4 in the textbook if you want to read along. That's the only section we're going to cover, but there is a little announcement. You do have some new stuff up in WebAssign. So homework, was it homework 3? Was due Monday. If you need more time, request an extension. I just did that to try and keep us on schedule here so we're not shuffling things around too much. Homework 4 is out now. And that's due next Monday. There's also a quiz. Which will be due next Monday. Yes. All right. So we don't have our normal, we missed our Monday class. So normally our first homework of the week would be out on Monday, due on Wednesday. And I thought about posting a video, posting today's lecture in a video format and asking you guys to watch it, but I had a feeling that would create more problems than it solved. Because, you know, God forbid somebody miss it and then we've got half the class a lesson behind. We don't want to do that. So this is the vibe. We got plenty of stuff to do. Let's get to it. I can begin by writing down the definition or drawing a picture, but I really think this is one of those things where it's best to begin with an example. Oh, thank you, Shauna. Yeah, we are all feeling pretty good, She's pretty much entirely recovered. I've got a little bit of a sore throat. Our baby's a little bit congested, but everybody's doing sufficiently fine. Worst part of COVID for us, since we're luckily vaccinated, has been just having to isolate. So, one example. Our rate of change is speed or velocity. There is a slight difference between velocity and speed, and I want to get this out of the way now. Speed is how fast you're going. Velocity is how fast you're going and in what direction. So when we talk about speeds or velocities, we're always going to be thinking about motion along a straight line. Like in the example I'm about to describe to you guys, I'm going to get in my car and just drive north. It's an imaginary universe where there's a road out here that just goes north forever. We're never going along a curvy path. We're always just going straight. So velocity, if it's positive, means you're going that speed in the positive direction. And if your velocity is negative, then you're going backwards the other way. So speeds are always positive, but velocity can be positive or negative. And the velocity encodes a direction along with that sign. So one example we've seen this is speed. Imagine I get in my car and drive north. All right, that's it. Get in my car. Let's say at time X equals 0 hours. All right, so I'm like starting the clock the moment I get in the car. Okay. The function f is defined by the rule f of x equals the distance I am from my home X hours later. All right, so f of 1 would be how far I am from my house 1 hour after I leave. F of 3 would be how far I am from my house 3 hours after I leave. And if I say f of 5 is 0, that means 5 hours after I left, I've returned home. I'm 0 miles from where I am. Sorry, let me include the units here. This is in miles. All right, so I want to first make sure we're comfortable with what I'm saying by this function f. Are we? Any questions about the definition of f here? So the input variable x, that's time. How many hours has it been since I left? And the outputs are the distance I am from my home at that time. All right, so if 5 hours after I leave, I am 100 miles away, then f of 5 is equal to 100. If 10 hours after I leave, I am back at home, then f of 10 would be 0. I'm going to go ahead and draw a graph for this function. We're going to go on a trip together here, and then we're going to talk about some speeds. All right, so here is one hypothetical graph. Let's call this 50, 100, 150, 200, 250, 1 hour, 2 hours, 4 hours, 5 hours. Say 6 hours. All right. And maybe we start off, well, I've got to start off at the origin, right? Because I'm starting at my house. So at time x equals 0, I have to be 0 miles from my home. And then maybe after that first hour, I've made it about 100 miles. And we continue on something like this. That third hour, I'm about 250 miles away. And then we hang out there for an hour. Start to come home. Let's say it's the 7th hour. Yeah, let's do that. Okay. Oh. This looks pretty good. So I want us to be comfortable interpreting this graph. And then we're going to try to see what sort of geometric feature of this graph tells me about the speed or velocity I'm going at any moment here. So just to be clear, what we're saying is I started at home, and then over that first hour, I got 100 miles away. And then kind of keep going, keep going, keep going. By the third hour, I am 250 miles away. And then from hour 3 to 4, I'm still 250 miles away. So I'm actually standing still for an hour. And then I start coming back home, right? My y values are coming down, which means my distance from home is coming back down. And by the 7th hour, I am back at distance 0. The y value here is the distance. So the y value everywhere is the distance, and the x value everywhere is the time since I left. Remember that speed or velocity, these have units like a distance over a time. For example, 75 miles per hour. Remember the word per. Per really means to divide. When you think about what the word percent means, if anybody's taken any French or Latin, cent or cent is 100, right? So percent means out of 100. And that's why when you go to calculate a percentage, you divide that number by 100. Or why you skip the decimal place over twice, right? Because that's the same as dividing by 100. So every velocity has units like this, some distance divided by some time. So like you're driving on the interstate, you're going 75 miles per hour, or the speed of light is 300,000 kilometers per second, right? It's always a distance over a time. Looking at this graph, thinking about the units of the y values and the units of the x values, what sort of object here could tell me a speed or a velocity? How could I get a distance over a time? Just think back to some concept that you've seen in a previous algebra class. Where have you divided y values by x values? Don't think too hard. I'm sure you all know this.
Slope.
Slope, right? Every time you calculate a slope, you're taking a rise over a run, which is a y value. In this case, those would be distances in miles, divided by an x value, which in this case would be a time in hours. So if you calculate a slope anywhere in this particular xy plane, you're talking about a speed. That would be a distance, miles, divided by some time in hours. So to find a speed, and this is the last time I'm going to use the word speed, I'm going to use the word velocity in the future. From this graph, would mean dividing some y values by some x values, which would be a slope. So for example, and I think I've done something illegal here actually, because I think my average speed over that first hour might be higher than any speed limits in the United States. For example, my average speed in the first hour would be the y value here minus the y value here over the x value here minus the x value here, right? How far have I gone in that first hour? Well, I started at home, 0 miles from where I set off, and I ended up 100 miles away. So that would be 100 minus 0 divided by how long did it take me? I went 100 miles, it took me 1 hour over 1 minus 0. And remember the numerator here, this is in miles. The denominator here is in hours. So this would be 100 miles per hour. Don't tell anybody. I went a little too fast. And what is that slope exactly? Well, it's the slope connecting these 2 points. Right, it's the slope of the little dashed blue line there. Now, does that mean I was going 100 miles an hour during that first hour? No, when I first left, I was going very slowly, right? I gotta like start the car rolling forwards. But then you see here, this is getting steeper and steeper and steeper. And that's me going faster and faster and faster. So I start off going very slow. I end up going quite quickly. And then you see here where it sort of comes back down, it gets less steep. That's me slowing back down. But on average, over this first hour, because I covered 100 miles and it took me only 1 hour to do it, on average, I was going 100 miles an hour. Now, there's a fun relationship here between the average speed and the exact speed at any moment, right? If you were to look over at the speedometer, if you were in the car with me, you could look over at the speedometer and say exactly how fast I was going at any one moment. You can't get that information from this graph as easily. Henry, I subtracted the zeros here to kind of be evocative of a slope, right? You're used to seeing 2 y values subtracted over 2 x values subtracted. So the y values were 100 and 0, and the x values were 1 and 0. Later, when I do it between other points, these will not be 0. So I just want to show you where it's coming from. If I want to find the average speed from x equals 1 hour to x equals 3 hours, that would mean calculating the slope from this point to this point, right? I would want to take the distance that I covered from hour 1 to hour 3. Since at hour 3, I'm 250 miles from home, and at hour 1, I'm 100 miles from home, that rise would be 250 minus 100. And that run would be 3 minus 1. And again, the top is in miles, the bottom is in hours. So 250 minus 100, that's 150. And 3 minus 1 is 2. 150 divided by 2, that's 75 miles per hour. Sorry. It's a little bit. And it turns out there's lots of other rates of change that are interesting, right? Like if I'm filling up a bathtub, that water flow is coming out at some speed, right? Some number of gallons per minute. Or, you know, you can think of many, many different instances where rates of change are significant. If I'm looking at something spinning around, I can talk about how many revolutions, how many times it spins per minute, RPM, right? You see that in car engines. You've got a little thing called a tachometer that measures the RPM of your motor. If you give me 1,000 2x2x2 Rubik's cubes and ask me to solve all of them, you can figure out how quickly I'm doing that. You can say I'm solving 10 Rubik's cubes per minute. Obviously, I'm not going to do that, but many, many different rates of change. The nice thing is that if you have a function measuring the object that is changing, like here, f of x is measuring the distance I am from home, you have a function that measures the object that is changing, then the rate of change associated with that function will be the speed associated with whatever the action is. Now, in full generality, here's the definition. Mathematicians love this stuff. The average rate of change for the function f from x equals a to x equals b is f of b minus f of a divided by b minus a. Right, so this is like f of 1 minus f of 0, all divided by 1 minus 0. This was f of 3 minus f of 1 over 3 minus 1. I know that you're used to seeing slopes written as like y2 minus y1 over x2 minus x1. We're not going to do that anymore. Remember last week I said one of the big things that I'm like required to gatekeep in this class is function notation. And I'm going to show you some problems today where you really need to think of things this way. And I'll try to convince you that this is the superior notation and way to think of a slope when that slope is coming from a function's rate of change. So here's something you need to tuck in your pocket and remember forever and ever. Of course, everything I put on the document camera needs to go on your notes, but make sure you have this in there somewhere you can find it in the future, refer back to it as needed. I'd like to ask you, do you remember what this numerator is? You should look familiar. Think back to last week. There was a certain kind of change that we talked about last week. That was exactly this top. What was that?
Net change?
Yeah, the net change. So this is the net change divided by the length of the interval. The length of the interval from A to B. So if your inputs are time, then the length of the interval AB, the thing B minus A, that's the time elapsed or the change in the input. So it's like the net change in the output divided by the change in the input. That's what you have for an average rate of change. And that's where the word average is coming from. So the average is because you're dividing out by the length of this interval. We're saying this is how fast you are going on average between hour 1 and hour 3. If you want to talk about how fast you're going at any particular moment, let me return to that graph for just 1 second. If you want to get from this graph the speedometer information in my car, you want to know exactly how fast I was going at any one moment, what you would be looking for is like the slope of the graph at a point. And that's much harder to calculate. You can say down here, oh, the slope looks pretty shallow and the slope is getting steeper and steeper and steeper and then getting shallow and then kind of staying constant and then going straight flat, right? My slope here is 0 and then it's pretty flat here, it's negative. But actually finding the slope anywhere on this curvy portion at an exact point, like saying right here, right at this point right here, what's the slope? That's a question that is very, very hard. It requires calculus. And the way you do it is kind of by coming up with a formula for the slope of this blue line and then bringing both of those points closer and closer to this guy. So what we're calculating here are average rates of change. The speedometer would be giving you the instantaneous rate of change. And that's a somewhat trickier biscuit. There is a geometric interpretation here though. And that geometric interpretation comes with some vocabulary, so I'd like to share it with you. Graph a sort of generic looking function. This is f of x. And maybe I want to look from some x value over here, call A, some x value over here, call B. What we do is we think about those points on the graph. The average rate of change is going to be this rise over this run, which is the slope of this blue dashed line here. Which has a, maybe I won't dash it. We've got some color. If you're working without color, I suggest dashing this line. Since I've got the colors, solid, so it's easier for you to see. So the average rate of change for this function from x equals a to x equals b is this rise over this run, which is the slope of this line. So the average rate of change is the slope of this, and the line is called a secant line. I know some of you are taking trigonometry right now, or maybe took trigonometry last semester. The secant line in this sense, which is just a line that connects 2 points on a graph, the reason we call that line a secant line is connected to the secant function from trigonometry. If you look at the geometric definition of the secant function, it is the length of a certain secant line. You take your unit circle, plop it right at the origin, and then the secant of theta is the length of a secant line. Google geometric definition of secant if you want to see that. Okay, so a line connecting 2 points on a graph is called a secant line, and the average rate of change for a function over an interval where you've constructed a secant line is the slope of that secant line. And we always want to write it like this. Let's look at an example or two. Let's find the average rate of change for the function f of x equals parentheses x minus 3 all squared. We'll do a couple of these from x equals 1, so x equals 3, and from x equals 4 to x equals 7. And just for fun, I'm going to draw the graph of this guy. This is a function that you guys should know how to graph. We are going to go over it in a little bit of detail when we talk about transformations. But this is the same as the graph of x squared. It's just been shifted to the right by 3 units. So what does this look like? If I come over here, 1, 2, 3. That vertex will be there. Let's see what all this up here now. All right, so there's the graph. roughly. The y-intercept over here, if you care, happens to be 9. If you plug in x equals 0, you get 9 out. But let's do it. Let's calculate these rates of change. Here's our graph. We'll try to interpret those rates of change as slopes. So first, let's just see how we do the calculation. So the average rate of change is always f of b minus f of a over b minus a. So here, a is 1 and b is 3. All right, a is always the smaller number. B is always the larger number. So what's that going to be here? Well, this is going to be f of 3 minus, b is 3, f of 1 over 3 minus 1. I want to be very clear about this. The numerator here, this is function notation. This is the output from the function f when you feed it the input 3. This is not f times 3. This is f of 3. And similarly, this is not f times 1. This is f of 1. So there is nothing that can be canceled here. You cannot cancel the 3's. You cannot cancel the 1. You cannot factor out an f. None of that stuff is reasonable. Remember, just like last week when you had to compute f of 1 over x or f of a squared, all of those sort of things, think of this like those things. In fact, the only thing you can do with an expression like this, there's only one thing you can do, and that's plug in. You got to plug in whatever these things are. So what is f of 3? Well, I could come off to the side, plug 3 in here, maybe make a little table or a list of values and then do that. But the more grown-up way to handle this is to just say, okay, I know what f of x is. F of x is x minus 3 all squared, and that's for any x. So f of 3 is 3 minus 3 all squared. And then this minus is this minus coming from the formula here. What is f of 1? Well, f of 1 is 1 minus 3 all squared. And then downstairs, 3 minus 1, that's 2. Now, we just follow our order of operations, and you guys are going to become experts at order of operations stuff. We've got some parentheses with some powers up here, so we've got to manage all that crap first. So inside this paren, 3 minus 3, that's 0. So this is 0 squared minus, I'll put it in parentheses still, minus 1 minus 3 is negative 2. So that's negative 2 squared all over 2. 0 squared is 0, right? 0 times 0. Negative 2 squared is positive 4. So this is 0 minus 4. I'll write it over here. 0 minus 4 over 2, which is negative 4 over 2, which is negative 2. Remember this piece right here? This is f of 3. This piece right here, this is f of 1. So I'm just plugging in, right? I've got the formula, I've got the explicit algebraic definition of f of x. So if I want to know what is f of 3, I just plug in a 3 for x. The slope of the line that we're looking at here, this is not the slope of the black curve. The black curve does not have a slope, it's curvy, right? The slope is changing all the time along that black curve. Otherwise, it would be a straight line. But the slope that we're calculating there is the slope of the secant line connecting this point to this point. That's the slope of this blue dashed line here. And you see that this line has a negative slope, right? It's pointing down. It makes sense that this would come out negative. Your average rate of change can be negative, can be 0, and can be positive, just like your net change. And in fact, the rules are exactly the same because the sign of the denominator is always positive. B is always the larger number, A is always the smaller number. So the downstairs here is always going to be positive, which means that the sign, positive, negative, 0, of the average rate of change is really just the sign of the numerator. And remember that numerator is net change. And we talked about when this is positive, when it's negative. If f of b is bigger than f of a, if you've overall gone up over that interval, then this will be positive. And if f of b is smaller than f of a, that would mean overall you've gone down on that interval. That means this will be negative. Any questions on the calculation here? Okay, let's look from 4 to 7 then. Again, I'll start just with the recipe. The average rate of change is always f of b minus f of a over b minus a. And in part b, a is 4 and b is 7. So this is going to be f of 7 minus f of 4 divided by 7 minus 4. And just like with the last guy, it is true, you could go off to the side and calculate f of 7, go off to the side and calculate f of 4. But I'd like you guys to get used to doing things this way. And in the next problem, I'll show you why that's the necessary way sometimes. So here I'm just going to say, okay, f of 7, that's 7 minus 3 all squared. Minus f of 4, that's 4 minus 3 all squared. And we're dividing by 7 minus 4, which is 3. And from here, everything's going to go just like it did in the last guy. 7 minus 3, that's 4. So that's 4 squared here. This minus is this minus. 4 minus 3 is 1. So that's 1 squared there. And we're dividing everything by 3. Four squared is 16. 1 squared is 1. So this is 16 minus 1 over 3, which is 15 thirds, which is 5. And the step where things might look a little weird, or you might ask yourself, where is that coming from? Just remember, this is f of 7. This is f of 3, sorry, f of 4. So really, I'm just plugging. I don't have space on the page here to draw the line whose slope we're calculating. The 4 comma f of 4 point is right here, but the 7 comma f of 7 point is way up off the top of the page. But you can see that from 4 to 7, if you were to draw that line in, it would, it would look something like this. All right, it would be going up quite steeply. So getting a positive 5 out here is not surprising. Just for fun, can we find the equation of this secant line here? This one, the blue one that we drew in earlier. So let's call this a bonus. This is certainly something I could ask you to do on a test. I could say, find the equation of the secant line to this function from this x value to that x value. So I'm going to find the equation of the secant line, to f of x equals x minus 3 squared from, will be the one that we started with, x equals 1 to x equals 3. That's what I'd like to do. What two things do I need to find the equation of a line? What are those two things?
Slope and intercept.
Slope is definitely correct. I need the slope. And here my slope, we've already found, right? Remember, the slope of this blue line is the average rate of change from 1 to 3, which we calculated earlier is -2. The average rate of change is the slope of the secant line. The other thing we need, the y-intercept will work. If I knew the y-intercept of that blue line, I could use that. From my picture, it looks like it's a little smaller than 9, but that's all I can say. So here's a big thing. We need to broaden our world of lines to think beyond mx plus b. Really what you need is the slope and any point on the line. So there's 2 points that I know for sure on this line, rather than trying to like guess, say, oh, I go over 1, I go up 2, I go over up 2. I can just take any point that I know is on the line. Here, one very obvious point on the blue line is 3, 0. So I'll call it just x1, y1, 3, 0. So I don't have the y-intercept, but I can still write down the equation of the line using the point slope form of a line, which is y minus y1 equals m times x minus x1. In this class, we're not too crazy about working with linear functions. We're going to work with lots of more exciting functions. But trust me when I say you need to broaden your world from mx plus b to this thing. Think about it for a second. If you know the y-intercept, that's the point 0, b. That means x1 is 0 and y1 is b. So this would be y minus b equals mx, which is the same as y equals mx plus b. This includes mx plus b. But it also allows you to find the equation of a line with the slope and any point on the line, even if it's not the y-intercept, which is dope. It's so much faster and easier. So slope is -2, point is 3, 0. That's y minus 0 equals -2 times x minus 3. All right, x1, y1. Y minus 0 is just y. And distributing the -2, you get -2x plus 6. So that y-intercept would have been 6. I didn't know that, but now I do. So here is the equation of that blue secant line. In calculus, you're going to be finding equations of tangent lines a lot, and you'll be doing that by thinking of them as limits of secant lines. So this procedure is going to be relevant there as well. All right, any questions on finding the equation of the secant line? I'll say again, hint, hint, nudge, nudge. This would make a good exam question. Any questions on calculating the average rates of change? Okay, so again, follow the recipe. Figure out what A and B are, plug in, and simplify. I think the challenge is twofold, mostly in the simplification, but also in making sure you plug in correctly. And this next problem is it's a little bit tougher. So imagine, imagine I'm totally fed up with pre-calculus. I take my book, my pre-calc textbook, to the edge of the Grand Canyon. And at time t equals 0, I throw, or not throw, I guess, drop the textbook off a cliff. Sure. All right, I'll come back here, finish writing. I'll describe the next example to you. So at time t equals 0, I drop the book off a cliff. It is a fact of physics, consequence of Newton's laws, that book will accelerate with a constant acceleration towards the Earth. That acceleration is determined by the mass of the Earth. In SI units, that book is going to accelerate towards the Earth at 9.8 meters per second squared, which means every second that book will gain a speed of 9.8 meters per second. Now, here in the United States, we usually work with feet rather than meters. So at time t equals 0, I drop the book off a cliff. The distance the book has fallen after t seconds is given by, I'll call it d of t for distance. T is my variable here, it represents time, and I'm using, instead of f of x, d of t, d for distance. This is 16 t squared. So 9.8 meters per second, or 16 feet per second. This is feet. So if I want to know how far down the canyon is the book after 1 second, you plug in t equals 1. If you want to know how far has the book fallen after 5 seconds, you plug in t equals 5. Is everybody comfy with what this function is telling us? It's a lot like the function from our first example, where that function told you how far I am from home. This tells you how far the book has fallen. All right, in this context, I would like to calculate 2 rates of change. I'd like to find the average speed of the book from t equals 1 second to t equals 5 seconds. That's not hard. That's just like the last example. Just remember that the average speed is the average rate of change for the distance function. Now, I could say average velocity here instead of speed. But then I want to do something a little harder. I want to find a formula for the average speed over a very generic interval. from some time, call it t equals a, to some time a little bit later, call it t equals a plus h seconds. So in part B, what we're doing is we're finding a formula for the average speed of the book over a small time interval from some generic time to some generic time a little bit later, right? We think of h as a small positive number usually. So t equals a, if you plug in, 1 and 1 for a and 4 for h, then that would give you the thing from part A, because then you'd be going from 1 to 5. If you plug in 1 for a and 0.3 for h, then this would be from 1 to 1.3. The object we're constructing in part B is the difference quotient. But first, let's go ahead and knock out the easy one. Are there any questions about what it is we're doing here? Okay, so for part A, we're looking for the average rate of change from t equals 1 to t equals 5. So here's A is 1, here's B is 5. And my function is D. So this is going to be D of 5 minus D of 1 divided by 5 minus 1. And again, this is function notation. You cannot factor out a D, you cannot cancel the 5s, can't do anything like that. The only thing I really can do with this is plug in. What is D of 5? What is D of 1? Well, D of t in general is 16t squared. So D of 5 is 16 times 5 squared minus D of 1 is 16 times 1 squared. And that downstairs, 5 minus 1, that's 4. There's a bunch of ways to try and simplify an expression like this. Let me show you the smart way. All right, the kind of naive or obvious thing to do here is to say, okay, 5 squared is 25, 16 times 25 is some big number, I don't know, let me get out my calculator. 1 squared is 1, 16 times 1 is 16. Okay, so I'm gonna use my calculator to compute this, and then I'm gonna use my calculator to subtract, and then I'll use my calculator to divide. Fuck that noise. We don't want to be chained to our calculators, and we need to be able to simplify complicated things like this without them. So how do we do that? Well, yeah. Let's deal with the parentheses and exponent stuff first, according to our order of operations. This is 16 times 25 minus 16 times 1 all over 4. But then instead of multiplying the 16 and the 25, there's a smarter move here, which is to factor out the 16. Look, here's one term. This numerator has 2 terms. The first term is 16 times 25. The second term is 16 times 1. There's a common factor of 16, which I can bring out. And then what I'm left with is 25 minus 1. And all of this is over 4. Now, 25 minus 1, that's 24. So this is 16 times 24, all over 4. And you might be thinking, okay, now I need to multiply 16 and 24. No, you don't. No, you don't. Look, 16 is 4 squared. So you've got 4 squared times 24 all over 4. You can cancel the 4s. Alrighty, this is like 4 times 4 times 24, all divided by 4. So you can cancel one of these with this. 4 is a factor of the top and a factor of the bottom. Common factors top to bottom can be canceled. So then you just have 4 times 24 left over. 4 times 20 is 80, 4 times 4 is 16, so this is 80 plus 16, which is 96. No big numbers anywhere, no calculator required.
So can we not factor that 24?
You could, yep, you could write this 24 as a bunch of different ways. You could write it as 6 times 4, and then you could cancel that 4 instead of canceling this 4. And then you'd be left with 16 times 6, which is also 96. We could write 24 as 8 times 3 and then cancel the 8 and the 4. Lots of different ways we can approach this. All right, so what does this mean? This means that over the time interval from 1 second to 5 seconds, the book is falling at an average speed of 96, and this is feet per second, which is pretty quick. Feet per second is a weird unit of speed. It's not something that we're used to using a lot, unless maybe you are into like paintball. I think paintball, they still use feet per second as the unit of speed. So if you've ever gone paintballing, I think usually the markers that they'll rent to you have a muzzle velocity of something like 200 feet per second. It's about half as fast as a paintball. It's pretty quick. Book's falling at a good clip here. Any questions on the calculation or the simplification, any of that? Okay, part B is a little bit more challenging. So for part B, let me grab a fresh piece of paper here. A little more space for it. Here what I'm looking for is the average rate of change from t equals a to t equals a plus h. I don't know what a is, it's just some constant. I don't know what h is, it's just some other constant. So I'm not going to be working with numbers here. I'm going to have some symbols, algebra, that I need to simplify. So here's a is a, and here b is a plus h. So this is d of a plus h minus d of a, all divided by a plus h minus a. The same recipe, right? F of b minus f of a over b minus a. It's just that instead of f, now my function is called d. And my b value is this generic a plus h thing. This is the difference quotient from last week's homework. You saw lots of these there. And the big thing is making sure you handle the d of a plus h piece correctly. Downstairs, a plus h minus a, that's just h. So all of those difference quotients from last week's homework, they were really rates of change. I want to make a little note here. D of a plus h is not d of a plus h like this. I cannot just take this function, plug in an a here, and then add a plus h on the outside. That doesn't work. And it's also not the same as d of a plus d of h. That's not true in general. So what is d of a plus h? What is this very first piece upstairs here? Well, d of t is 16t squared. D of dog shit would be 16 times dog shit squared. D of your mom is 16 times your mom squared. So d of a plus h is 16 times a plus h squared. D of a is 16a squared. And h is just h. So this and only this is the correct way to begin. And I think the place where people most often make a mistake is writing this piece as anything other than this. But when you look at the definition of the function d of t, it should be pretty clear that d of a plus h is 16 times a plus h squared. Remember, anytime you're evaluating a function, you just plug in for the variable, and you do so in parentheses. If I was being very, very careful, I would write this as 16 times parentheses a squared, but we know parentheses a squared is just a squared. Okay, how do I simplify this? What can I do to clean this up?
Do you factor it?
Yeah, look what we did here. I had a common factor of 16 that I could pull out. Here, I have a common factor of 16 that I can pull out. Let's do that right away. By factoring that 16, I'm able to reduce the size of the numbers that I'll have to deal with here. But then there's still something left over. I got to manage that a plus h squared minus a squared. I got to clean up that inside. So don't write this down. I have a question for you. True or false?
False.
False. Why? So you're correct. Yes. Yeah, true is correct. This is not a true statement. This is false. Why is this false?
Because you're missing the middle component, the AH.
Good, very good. So remember, a plus h squared is a plus h times a plus h. Anything squared is that thing times itself. And to calculate such an object, you need to FOIL. So this is a squared plus ah, which is plus 2ah plus h squared. So this is not true. So we come back over here. This is 16 times this piece, a plus h squared, which is a squared plus 2ah plus h squared. And then, oh, I've got a minus a squared here. That's nice. All of this is being divided by h. Positive a squared here and the negative a squared here eat each other up. And I get 16 times 2ah plus h squared over h. So one of the questions I get a lot when we talk about problems of this sort is, when should I stop? What is enough simplification? When you're dealing with a difference quotient like this, an expression that's like f of a plus h minus f of a all over h, remember what I said a minute ago about instantaneous rates of change versus average rates of change. We bring those 2 points together and we get an instantaneous rate of change. Well, the separation between the 2 points, the one that comes from t equals a and the one that comes from t equals a plus h, the separation between those two is just h. So in the long run, what we'd like to do is send h to 0. So what we really have a problem with here is the fact that there's an h in the denominator. So on these sort of problems, what you want to do, your goal is to get rid of the h downstairs. So here we're not quite done. I'd like to do just a little bit more. Does anybody see anything else I could do to simplify this with the idea in mind that we want to get rid of the h from downstairs?
Would we multiply to get rid of the h or no?
Let's see. So it's true that dividing by h is the same as multiplying by 1 over h. That's one way we could think about this. But there's a slightly better way.
Could
Did you pull an h out?
Yeah.
Yes, very good, very good. So there's the numerator here has this chunk. This chunk contains two separate terms, h squared and 2ah, both of which have a factor of h. So if my long-term goal is to cancel the h downstairs, what I need to do is factor an h from the top. Remember, the rule is you can cancel if and only if you can factor. So we should try to factor an h out from the top. And since both this and this have an h in them, I can factor an h, and what's left is going to be 2a, right? If I were to redistribute this, 2a becomes 2ah plus h. So this h I have factored out from this piece, right? If I were to redistribute this, it would become this. But I'm not going to redistribute it. The whole reason I factored it out is so I can cancel it with the h in the denominator. So here I get 16 times 2a plus h. And you could distribute the 16 if you want, or you just leave it like this. This is done. So we now have a nice formula for the average speed or average rate of change over any sort of interval. You can plug in whatever a and h you want and get out the average speed over a particular time interval. Like I said, if we plug in a equals 1 and h equals 4, then this would give me the answer to part A. So if you had somebody asking you for like 30 different average rates of change, 30 different speeds for this book as it falls, it would be better to come up with this formula and then plug in the various a's and h's rather than calculating each of those separately. Okay. Any questions on the calculation here in part B? Alrighty, let's see how we're doing for time. There's one other thing that I want to talk about today, but I think we are right at time now. So let me wrap up. Give me just a few more seconds of your time to make an observation. This observation has to do with average rates of change and increasing and decreasing function. I'm going to make a statement. I'm going to share a fact with you, and then I'm going to ask you a question, and I'll let you go. So if f of x is a function, if f is an increasing function, or if f is increasing on the interval ab, maybe something like this. A is over here, B is over here. If your function is increasing everywhere on the interval from A to B, then the average rate of change on that interval for that function will be positive. And kind of thinking about it the other way, if f is decreasing, on the interval AB, then that average rate of change has no choice but to be negative. All right, the dashed lines here have negative slope in the second picture, positive slope in the first picture, and they can't help it. Can't help. But each of these statements have what's called a converse. If I tell you that the average rate of change is positive, can you conclude that f had to be increasing? Or if I tell you that the average rate of change is negative, can you conclude that f had to be decreasing? In other words, can I turn these arrows around? So the question I will leave you with, what about the converse? If the AROC is positive, must f be increasing? Or if the AROC, average rate of change, is negative, must f be decreasing? And this is a question that shows up kind of early in your homework. I suggest doing some of the other problems first. If you look at the other problems where you have lots of graphs to play with and you have lots of rates of change to calculate, you'll come up with the answer to this question quite naturally. So certainly the one direction is true. If you're increasing on the interval AB, then the average rate of change from A to B for that function will be positive. There's no avoiding that. If you're increasing everywhere on that interval, you will end up higher than you started. But just because your average rate of change is positive may not be the case that your function is increasing everywhere on that interval. You could imagine maybe this function, instead of just going up all the time, it wiggles in here a little bit and then goes up. So I'd like you to think hard about this question as you work through the homework problems. Don't feel obligated to answer it right away, but look at some of the other problems and see if you can come up with a good answer. It turns out to be a little bit subtle. There are very meaningful connections between the sign of the rate of change and the monotonicity of the function, but they're not obvious, not obvious. All right, that's where I'm going to leave it for today. Reminder, you have a quiz and a new homework in WebAssign. Here's the current docket. So you've got homework 4 and quiz 1. These are both due for you guys on Monday of next week, which is our next class meeting. If you need to talk to me about anything, you can come by office hours. I have one today from 1 to 2 p.m. You can send me a Canvas message. You can go on the Discord. I think that's it. All right. Take care, guys.